Deep beneath our feet lies a realm so extreme it defies imagination. While we walk on solid rock, a furnace the size of a planet's heart smolders at temperatures that eclipse the surface of the sun. This is the story of Earth's core, its composition, its history, the methods we use to glimpse the invisible, and the profound impact it has on everything from magnetic fields to volcanic eruptions. The concept of a molten center dates back to the early 19th century, when pioneers such as Pierre Bouguer and William Thomson, Lord Kelvin, first attempted to calculate Earth's internal temperature from seismic data. Their bold equations suggested a core hotter than a furnace, but the tools of the age were crude, relying on surface observations and simple wave travel times. It was not until the invention of the seismometer in the 1900s that we could truly listen to the planet's inner symphony. When an earthquake shakes the crust, seismic waves cascade inward, refracting, reflecting, and sometimes disappearing entirely. The way P waves speed up and S waves vanish at a certain depth gave scientists the first clear sign of a solid inner sphere surrounded by a liquid ocean of iron. Modern global networks now capture millions of such tremors each year. By triangulating these signals, researchers have mapped a layered interior, a thin crust, a viscous mantle, a liquid outer core extending roughly 2,200 kilometers, and a solid inner core about 1,200 kilometers across. The inner core, though solid, remains as hot as 5,700 Kelvin, comparable to the surface of the Sun. Why does the inner core stay solid at such temperatures? The answer lies in pressure. At the planet's center, pressures exceed 3 million times atmospheric pressure, crushing iron atoms into a tightly packed lattice. This immense pressure offsets the thermal energy, preventing the metal from melting, much like a diamond remains solid under the weight of the Earth itself. The outer core, however, cannot withstand the same pressure, remaining a turbulent sea of molten iron and nickel. As this liquid metal churns, the Coriolis forces from Earth's rotation organize it into massive, spiraling columns. This geodynamo generates the planet's magnetic field, a protective shield that deflects solar wind and preserves our atmosphere. The magnetic field is not static, it waxes, wanes, and even flips polarity over geological timescales. Paleomagnetic studies of ancient rocks reveal reversals occurring every few 100,000 years. These flips are thought to be linked to changes in the flow patterns of the outer core, a reminder that the core's dynamics directly influence the surface environment. Beyond the magnetic implications, the core's heat drives mantle convection. As the outer core releases thermal energy, it creates temperature gradients that cause the overlying mantle to circulate slowly, like a giant, planetary lava lamp. This convection underlies plate tectonics, the relentless motion of continents, and the formation of mountains, earthquakes, and volcanoes. Our understanding of the core's composition has been refined by studying meteorites, particularly those known as iron meteorites. These space rocks are considered fragments of ancient planetary cores, offering a tangible sample of the alloy mixtures that likely dominate Earth's interior. Analyses reveal trace elements such as sulfur and nickel that affect melting points and density. Recent advances in neutrino detection have opened a new window into the core. Geoneutrinos, subatomic particles emitted during radioactive decay of uranium, thorium, and potassium deep within Earth, can be measured by detectors buried deep underground. Their flux provides indirect clues about the amount of radiogenic heat contributing to the core's temperature budget. Explorations of the core are not limited to passive observation. In the 1970s, the Soviet Union's Luna 24 mission retrieved a core sample from the Moon, demonstrating the feasibility of drilling through a planetary crust. While we have yet to send a drill to Earth's own core, an endeavor that would require a shaft over 6,000 kilometers deep, the ambition fuels ongoing research into ultra-high-temperature materials and autonomous drilling technology. The notion of a journey to the core has also captured the public imagination, from Jules Verne's speculative novels to modern science fiction blockbusters. Yet beyond storytelling, these ideas inspire real scientific challenges: how to protect equipment from temperatures hotter than the sun's photosphere, how to communicate across thousands of kilometers of solid rock, and how to harness the immense pressures for experimental study. Understanding the core is vital for predicting future changes to our magnetic field. As the inner core grows, solidifying a fraction of the outer core each year, it subtly alters the geodynamo's behavior. Some models suggest a weakening field could increase radiation exposure at the surface, while others warn of potential rapid reversals. Monitoring these trends is essential for modern technology dependent on satellite navigation and power grids. In the grand narrative of planetary evolution, Earth's core stands as both engine and archive. Its composition records the early solar nebula, its temperature chronicles the planet's cooling over billions of years, and its motion writes the magnetic script that shields life. As we continue to refine our tools, seismic tomography, deep mantle sampling, neutrino astronomy, we draw ever closer to fully reading this hidden chapter. The core remains a frontier, a secretive furnace whose heat surpasses even the brightest star we see each day. Yet through ingenuity, patience, and the relentless pursuit of knowledge, humanity inches toward the center of our world. The next breakthrough may come from a tiny particle, a daring drill, or a new mathematical model, but one truth endures: the heart of Earth beats hotter than the sun's surface, shaping the very surface upon which we stand. Beneath the crust, the mantle churns like a slow-moving ocean of molten rock, its convection currents driving the drift of continents. These currents are powered by the relentless heat escaping from the core, and their patterns are recorded in the magnetic anomalies that line the ocean floor, a silent ledger of Earth's inner furnace. The core's heat also fuels the geodynamo, the colossal dynamo that generates our planet's magnetic field. As liquid iron swirls at thousands of degrees, it creates electric currents that shield life from solar radiation, a protective bubble forged deep within the planet's heart. Scientists have turned to neutrinos, ghostly particles that pass unhindered through rock, to peer into the core's temperature. By measuring the faint glow of geoneutrinos, they hope to map the distribution of radioactive elements that act as the core's hidden furnace. In the realm of engineering, the quest to drill deeper has birthed the Superdeep Borehole projects, where steel strings of drill pipe descend past 10 kilometers, confronting pressures that would crush ordinary equipment, all to retrieve pristine samples of the mantle's composition. Beyond Earth, the heat of planetary cores dictates the habitability of worlds beyond our own. Mars, once warm enough to host rivers, lost its dynamo and magnetic shield, allowing solar wind to strip away its atmosphere, a cautionary tale written in the cooling of a planet's interior. Even the most violent volcanic eruptions are surface expressions of the core's energy. When magma breaches the crust, it releases gases and heat that can alter climate, fertilize soils, and reset ecosystems, reminding us that the core's pulse reverberates through every layer of Earth. Emerging quantum computing models now simulate the behavior of iron under core conditions with unprecedented precision, revealing subtle phase transitions that could explain anomalies in seismic wave speeds and the mysterious inner core superrotation observed by seismologists. Ultimately, the heat at Earth's center is a reminder of our planet's dynamic youth, a legacy of planetary formation that continues to shape climate, technology, and even the future of deep Earth mining. As we harness that knowledge, we stand poised to turn the planet's own fire into a source of sustainable power.